on this computer. Now, before I go ahead with the lesson, allow me to delete one person here who is failing to use the correct name. So we are looking at the chemistry of group 7 elements, or the chemistry of halogens. In our previous lesson, if I'm to make a recap, we looked at electronic structures of these elements, and then we also made a general. We also looked at the general outermost configuration of them. We looked at the bonding and structure variation, if you do recall. And we explained why fluorine and chlorine are gases, whereas bromine and iodine, bromine is a liquid and iodine is a solid at room temperature. We went ahead to explain that. We looked at the variation in melting and boiling points and explained it in detail. Okay, we looked at variation in atomic and ionic radius. I told you to read about fast ionization energy. We looked at fast electron affinity in detail, and I told you should be aware of how to plot a graph of fast electron affinity if required, and explain that variation with the anomaly that occurs for fluorine. We looked at the bond dissociation energy of these elements. We looked at the various methods of preparation of chlorine and the general method for preparation of all of the halogens with the exclusion of fluorine. And we saw that chlorine can be prepared by about 6 methods, if you do remember very well. We looked at the chemical properties of these elements, in particular reactions with hydrogen. And we show that with the reaction with hydrogen, the reactivity increases down the group, as shown by the conditions for the reactions. I told you to emphasize the physical states of each of the reactants and the products formed, with emphasis that hydrogen fluoride is a liquid and other hydrogen halides are gases. We looked at the chemical properties, specifically the reaction of the elements with water. So we looked at how these elements react with water, with the fluorine being the strongest oxidizing agent, whereby it oxidizes water to oxygen and hydrofluoric acid. I told you the reaction of fluorine with water does not yield hydrogen fluoride. This is not hydrogen fluoride, as most of you normally write in exams, but it's hydrofluoric acid. Just because the hydrogen fluoride that would be formed dissolves in the water present, form an acid. Then the other two disproportionate to form corresponding halate 1 acids and hydrohalic acids, which you should name for each specific halogen here, emphasizing the states, chlorine being a gas, bromine being a liquid, and the reactions being reversible. That's very important. Hallelujah.
Yes, teacher.
What have I emphasized about reactions of bromine and chlorine with water?
You emphasized on the states of bromine and chlorine. Chlorine being a gas, bromine a liquid.
And what else?
That's what I had. I've just joined.
Let Alvin tell me what else have I emphasized about the two reactions. Alvin is not present. Frida, what have I emphasized about the actions of chlorine and bromine with water? Evelyn. Rebecca.
It says the reactions are reversible.
Very good. The two reactions are reversible. Jordan, you're saying something.
Yeah, and also they form the acids, not the gases.
Very good. Because of the presence of water. Iodine does not react with water. I went ahead and explained that. If you do very well, remember. And then we ended with the reactions of the elements with sodium hydroxide. We said with the cold dilute, when they tell you to describe reactions of these elements with sodium hydroxide, you must specify the conditions. For example, if sodium hydroxide is cold and dilute, you must know the reaction and products. Maybe just get me crest and anomalate. I won't take it today. It's late. So we are looking at reactions of these elements with the sodium hydroxide. You react cold dilute sodium hydroxide, which of the elements? So chlorine reacts with cold dilute sodium hydroxide, form oxygen difluoride, fluoride ions, and water. And I told you can consider any of the two reactions, whether ionic or molecular, so long as you can be able to balance it, but not both. The other three react in a similar way. The difference is in the states here, chlorine a gas, bromine a liquid, iodine a solid, but the products are almost the same, as long as the sodium hydroxide is cold and dilute. I went further and emphasized that the halate 1 salts formed undergo further disproportionation if heated or warmed, form chlorate 5 ions and chloride ions, bromate 5 ions and bromide ions, and the yellow solution turns colorless during the reactions. If the sodium hydroxide is hot and concentrated, the only thing that changes is the product. This salt here, instead of being a halate 1, it becomes a halate 5. For each of them, you must be aware of the balancing of these equations to be able to sit alone and try to rewrite them and balance them without looking at your notes. So today, I want us to look at the oxidizing action of the halogens. These halogens have variety reactions, a variety of reactions where they act as oxidizing agents. Kezia, are you following? Noelina. Noelina, are you following?
Yes, teacher.
So we are looking at the oxidizing action of the halogens. Mary, can you read for us the first question about that?
State what would be observed and explain your observations when chlorine and bromine are separately added to iron 2 chloride solution.
Very good. We want to know what shall we observe when we add chlorine and bromine to sodium to iron 2 chloride solution. Okay. We want to know what really happens when we add chlorine to iron 2 chloride solution. Sorry. So I've just told you the two are oxidizing agents. So by the fact that we're adding them to an iron 2 salt, there will be oxidation of iron 2 to iron 3. So what do you expect to be observed? What do you expect to be the observation? Can anybody predict the observation for that reaction? So nobody can predict the observation for the reaction. Okay. What's happening? What's really happening? I'm having issues with the screen share here. I don't know where the problem is. So when you add chlorine or bromine to an 2 chloride solution, this solution is green and 2 chloride solution is green. Chlorine is a greenish yellow gas, bromine is a red liquid. So in each of the two cases, this green solution turns brown, just because the iron 2 ions are oxidized to iron 3 ions. So the question tells us to state what is observed and then explain our observation. So our observation in each of the cases is that the green solution turns brown. And then what's the explanation? Chlorine or bromine oxidize iron 2 ions to iron 3 ions, as it is reduced to chloride ions or bromide ions respectively, depending on what you're using. So if you're using chlorine, it's reduced to chloride ions. If you're using bromine, it's reduced to bromide ions. And any question in chemistry that involves an explanation, which explanation is inorganic, and eventually will involve an equation, the equation should be part of your explanation. So after writing the explanation, follow that with an equation as shown below. Hope that's very clear, members. Aoya, is that clear? Jordan, is that fine?
Yes, teacher, it's fine.
All right. So I can now proceed. These are redox reactions, but they are showing specifically the halogens being oxidizing agents. When you bubble chlorine through potassium nitrite solution, what happens? You're saying chlorine is bubbled through potassium nitrite solution and then silver nitrate is added. Sometimes these questions cheat for you the answer even before you do them. When you see silver nitrate here, you must know what it's going to test for. Silver nitrate is normally used to test for chloride ions or bromide ions or iodide ions. In this case, because of the chlorine is likely to dissolve to form chloride ions, which will now react with the silver nitrate to form silver chloride that ends up as a white precipitate. Then, in this species, potassium nitrite, by the way, members, have you looked at what we call redox reactions before? Did you look at redox reactions?
No.
You didn't.
Yeah, part of it.
If you haven't looked at redox reactions, then this is a bit disturbing. But redox, because we need some knowledge on how to write some of these reactions. However, if you have it, let's just look at them. We shall emphasize how to derive the redox reactions from these half cell reactions. So what we need from the potassium nitrite is nitrite ions alone. It is these nitrite ions that are going to react with the chlorine in presence of water, form chloride ions and nitrate ions, as you see here. The nitrite ions are oxidized to nitrate ions, and the chlorine is reduced to chloride ions. It's now these chloride ions that react with silver ions to precipitate or to form insoluble silver chloride that will appear as a white precipitate at the end. So what's our observation in this case? The greenish yellow gas dissolves, that's the chlorine gas, and the colorless solution is that the potassium nitrite solution forms a white precipitate. What's that white precipitate? That white precipitate is silver chloride. It's soluble in excess ammonia and form a colorless solution. But in this case, we don't have to add this because nobody talked about excess ammonia here. Unless the excess ammonia is being talked about in the question, then that's when you emphasize it. But if it's not given, then don't have to emphasize it. Is that very clear? Have you understood the concept? Members, you're not responding.
Teacher, a bit.
So if that's
Teacher, please repeat.
from where specifically?
Teacher, the explanation.
Explanation. So here, chlorine is an oxidizing agent. It oxidizes, this should be nitrite ions, not nitrate. It should be nitrite ions. So it oxidizes nitrite ions to nitrate ions. And it's self-reduced to chloride ions. Just have this equation the way you see it here. We shall have more time to see how to derive the equation. course, it may be hard for some of you to balance it if it's given like this. For now, get the concept. Later, we shall see how to balance the equations. So these chloride ions now formed are the ones that react with silver ions to form this insoluble silver chloride, which is now the white precipitate we are talking about here. I hope now it's a bit more clear. Can I proceed?
Yes.
Okay.
Yes.
So we are now bubbling chlorine through sodium sulfide solution. And after bubbling it through sodium sulfide solution, then we add barium nitrate. So just as the last equation we have seen, the barium nitrate is here to test for sulfate ions by formation of a white precipitate. But the sulfate ions are formed from the oxidation of sulfite ions from sodium sulfate. What oxidizes the sulfite ions to sulfate ions is the chlorine. Excuse me. So the observation is that the greenish yellow gas dissolves and the colorless solution. What's that colorless solution? The sodium sulfite solution forms a white precipitate. This is not supposed to be part of this. Forms a white precipitate with barium nitrate. This shouldn't be there. Forms a white precipitate with barium nitrate. So that should be the observation. So the greenish yellow gas dissolves and the colorless solution forms a white precipitate with barium nitrate. So what happens is the explanation here now. Chlorine oxidizes sulfite ions to sulfate ions. So the sulfite ions are oxidized to sulfate ions. And when they are oxidized to sulfate ions, the chlorine itself is reduced to chloride ions. So the chemistry here is oxidation reduction. That's what we should be talking about. Oxidized sulfide ions to sulfate ion is self-reduced to chloride ions. Then barium ions react with sulfate ions, form insoluble barium sulfate. So that's what we should be talking about. So the chlorine oxidizes sulfite ions to sulfate ions, it's self-reduced chloride ions. So these are the sulfite ions forming sulfate ions. The chlorine gas is reduced to chloride ions. So these hydrogen ions are from the hydrochloric acid being formed as a result of dissolution of chlorine in water. Now the barium ions react with the sulfate ions formed here, form the insoluble barium sulfate. That's what appears as the white precipitate. Is that clear? Members, is that clear?
Yes, teacher, it's clear.
Yes.
So the other oxidizing reaction of chlorine is seen here. We are bubbling chlorine through potassium manganate 6. This is not manganate 7. It's manganate 6. What everybody should be aware of is that potassium manganate 6 is a green solution, whereas potassium manganate 7 is a purple solution. So what will happen here is that this green solution will turn purple. Why does it turn purple? It's because the chlorine is an oxidizing agent. It oxidizes the manganate 6 ions to manganate 7 ions, which are purple. So now we add acidified tin 2 sulfate solution to the resultant solution. So the manganate 7 ions now will oxidize these tin 2 ions here to tin 4 ions, as shown by this redox reaction shown below. So what is our observation? The greenish yellow gas, which gas is the chlorine, dissolves in the green solution, which is the potassium manganate 6 solution, which the green solution now turns purple. But then it eventually turns colorless due to the explanation we are seeing here. Chlorine oxidizes manganate 6 ions to manganate 7 ions, and is self-reduced to chloride ions. So the chlorine gas is here oxidizing the manganate 6. Calculate the oxidation state of manganese here is +6. This is manganate 7. The chlorine is being reduced to chloride ions. Then the manganate 7 ions that we have formed here are the ones that oxidize tin 2 ions to tin 4 ions, as the manganate 7 ions are reduced to manganese 2 ions. So there are 2 redox reactions in one, but one proceeds after the other. That's not a common reaction, but I thought of it as being an important one too. Is there any question? No, Erin, is everything clear for you?
Yes, teacher, it is.
How about patience?
Yes,
Casey, are you following?
Teacher, I'm following.
Can I proceed?
Yes, teacher.
Okay. So we are further looking at still the oxidizing reactions. We are looking at reactions of chlorine, bromine, and iodine with sodium. thiosulfate, hydrogen sulfide, and then sulfurous acid. So chlorine and bromine will oxidize thiosulfate ions to sulfate ions as they are reduced to chloride ions and bromide ions respectively. But for these two reactions to occur, the chlorine or bromine must be in excess. So these are to call from the sodium thiosulfate, we are only interested in the thiosulfate ions, which end up forming sulfate ions. The chlorine and bromine form bromide and chloride ions respectively. I told you how the hydrogen ions come about due to the result of hydrochloric acid and hydrobromic acid that will be formed in each case. So for now, look at these reactions the way they are. We shall later see how to derive them from past half cell reactions and be able to balance them easily. However, if you can write them at this point and balance them easily, the better. So these two reactions occur if excess bromine and chlorine are used. However, if you use limited chlorine or limited bromine, then the thiosulfate ions will disproportionate into sulfate ions and sulfur. In other words, we shall have to form a yellow precipitate or a yellow solid deposit of sulfur. That's the difference. In addition to the products we have here, we shall have to add sulfur if we are using limited chlorine, because the oxidation will not be complete. Okay? So this is the reaction that will occur if we use limited chlorine. If the chlorine is in excess, then these are the two reactions that do occur. That's with thiosulfate ions from sodium thiosulfate. However, if iodine is being used, it's a weak oxidizing agent. It will only oxidize the thiosulfate ions to tetrathionate ions. We call these tetrathionate ions, and the iodine itself being reduced to iodide ions. Is there any question at that point?
Excuse me, teacher.
Yes, Gideon, excuse.
I've noticed that in most of these redox reactions, we always add water in the equation. Why is that so?
The water is from the solution is being used. Here, sodium thiosulfate solution has some water in it. Let me start a new share and see if you'll easily understand this. The problem is with my whiteboard. It doesn't easily work up very well. So if I have chloride ions, giving me, actually it is chlorine, not chloride ions. It is chlorine gas. Giving me chloride ions. So these chloride ions are two of them. I'm to balance the equation. Sorry. This is, we have two chloride ions here. Is that okay with you, Gideon?
Yes, sir.
That's with the chlorine gas. Now to balance this reaction, I must add the 2 electrons this side such that I balance the charge. The atoms are balancing. By this side I have a negative charge of 2, here this side I have a charge of 0. So I'll add the 2 electrons here. Balance the equation. Is it clear up to that point?
Yes, sir.
Now, if I'm considering sodium thiosulfate, thiosulfate is S2. You remind me, I've forgotten. Is it S2O4? Yes, S2O4 2 minus. This sodium thiosulfate, we are aware, I'm trying to derive how we get that equation. The sodium thiosulfate forms sulfate what? Sulfate ions. Is that clear with you?
Yes, sir.
Now we want to balance this equation and then combine the 2 equations. How shall I balance this equation? Look at this. We have 2 sulfur here, yet this is 1. You see that?
Yes.
Teacher,
Yes, please.
teacher, don't take three. Take three, not extra.
Oh, sorry. This is S3. This is S3. And then this is, no. Sorry. Undo. This is S2, and then this is O3. That's a thiosulfate. S2, O3. Yeah, thanks for that observation. Now, to balance this equation, I need to look at both the reactant side and the product side and see how many oxygen atoms are on the reactant side.
Three.
And how many now on the product side?
4.
So I must try to balance this reaction in terms of oxygen atoms. That's how water comes in. You get me now?
Yes, sir.
So this water is brought here to balance the oxygen, as you see on your screen. So that now I have my 4 oxygen atoms. Do you see that? Which are balancing with this. So the purpose of the water is to introduce the oxygen atoms here that balance
Yes.
the equation. However, still introducing hydrogen here means this side I must also introduce hydrogen ions, which were not there. You realize that? You get that?
Yes, teacher.
Now remember, the oxygen atoms are 2, yet this side we only have 1. Now it is now the time to balance. There are 2 sulfur atoms here. You shall need a 2 here to balance the atoms of sulfur. The oxygens are 8, yet these are 3. You realize that? The oxygens have become 8, yet these are 4. You see that?
Yes, teacher.
So I will need to put a value here that makes these oxygen atoms this side also 8. Which value shall I have to put here?
5.
Yes, I'll have to put a 5 here. I thought you looked at redox reactions.
5.
Yeah, when I put a 5 there, now my oxygens are balancing. What is not balancing in this equation now? Which atom is not balancing?
The hydrogens.
Hydrogen.
What shall I have to put here?
10.
Very good. So I will need a 10 here. I want to return this rubber. Don't know where my pen has gone. I rarely use this white, so I'm failing to get my pen back. This thing where my pen is. My pen is not seen again. So I have to put a 10 here. This is a vanishing pen. Oh. I cannot see my pen anymore. So it is here. I'll have to put a 10 here. But first of all, let me remove this plus. This will help me do what I want to do. So I'll need a 10 here. Balance this equation. Is that clear? Members,
Yes,
inform me if you're following, right? Hello? Are you following? Hallelujah, are you following? Victor, are you hearing me?
Yes, teacher.
So the charge here is 10, positive 10 minus 4, which is 6. Yet this is a 2. So the charge here is 2 minus, and the charge here is positive 10 minus minus this charge here, which is negative 4. So it would be plus negative 4, but since it's negative, it is minus 4, giving me a 6. So this is a 6 here. What do I have to do? I have to balance the two charges. How do I balance the two charges? I must add a figure here that will give me negative 2. Which figure do I add to 8 to give me negative 2? Which figure do I add to 6 to give me negative 2?
Negative 8.
So it will be negative 8. Negative 8 means adding 8 electrons here, because the electrons are negatively charged. I'm trying to explain how the water comes about. And I'm aware you have already seen why we use the water in most of these equations. Have you realized that, Gideon? Yes. Now to combine the two equations, I must multiply this by 4. When I multiply it by 4, these electrons are going to become 8 and they will cross out. Kezia, what's your question?
Teacher, the charge balancing part is unclear.
Yes.
The part of balancing charges is unclear. Okay, I've not understood it.
Kezia, did you understand how we reached here? How we got to the 6?
That part, yeah, I kept that one.
Now we are looking at the charges. The charge here is 6, yet this is -2, right?
Right.
It is very hard for us to make it.
Okay, yeah, right.
It's very hard for us to make the -2 become 6. Because to make the -2 become 6, we shall have to do what? This is a -2. The -2, to make it a 6, make the -2 a 6, we shall have to, yeah, this is a bit disturbing. To make the -2 a 6, we shall have to do what? What do we add there? We must add 8 electrons.
Teacher, I'm still not getting.
Yes?
Okay.
Kezia, I'm not getting you.
I'm getting.
So when you add 8 here, you end up having -6. But there is no way you can add 8 electrons on the reactant side. Adding 8 electrons here will mean subtracting them. You have to make it -8, which is not good in excuse me, which is not good in balancing equations. When we add here, we subtract. When you subtract here, we add the electrons. So actually, the best way you can understand it, if this is the option you wanted to use, if I add the +8 here plus -2 to give me the -6, that means if I have added here, this will be a subtraction. I will have to write here -8 electrons. But instead of writing -8 electrons here, take this as if it's an equal sign, shift them this side to become +8 electrons. Have you got it now?
Yes.
So if you've got that, I want now to see how we get the general equation. How do we get the general equation? That's what I want us to see. So the general equation will now be, we have multiplied this by 4, and multiplying it by 4 was to make these electrons become 8. So what happens now? This becomes 8. If I'm to recheck it, this is now 8 electrons. This is now 4. This is now also 8. Is that okay? So now we combine the two equations to come up with one equation. When we combine the two, what happens? When you combine the two, these 8 electrons cross out. We are delaying here a bit. These 8 electrons cross out with these ones. Remember, there was a positive charge here. So add the reactants here, put them on the reactant side, add the products, put them on the product side. You finally come up with this equation, that you're seeing here. Is that clear? Can I proceed?
Proceed.
So in most of those reactions, you will see that the water plays a balancing role. Its role is to balance the equation. Even this one, try it in your free time and see whether you can derive it. The water, its role is to play a balancing role in the reactions, and it comes from the solutions we use. There's always water in those solutions. Gideon, can you read for us these reactions? How do the halogens react with hydrogen sulfide?
Fluorine, bromine, and iodine oxidize hydrogen sulfide to deposit a yellow solid of sulfur as they reduce to corresponding hydrides.
Very good. So each of these will oxidize the hydrogen sulfide, which is a gas, to sulfur, a yellow solid, and end up forming the gases, corresponding gases. So that's not a new reaction to us. I remember at O level we must have looked at the first one here. Chlorine and bromine also oxidize sulfurous acid to sulfuric acid as they are reduced to hydrochloric acid and hydrobromic acid respectively. So you see the reaction here. You see the water still coming in. So the sulfurous acid is oxidized to sulfuric acid as the bromine and chlorine are reduced to hydrobromic acid and hydrochloric acid respectively. Is that also fine?
Yes, teacher.
So if that's very clear, it now takes me to the hydrides of these elements. Hydrides, we mean the compounds formed by the elements and hydrogen. The first hydride, the hydride of chlorine is hydrogen fluoride, the hydride of chlorine is hydrogen chloride, that of bromine is hydrogen bromide, and that of iodine is hydrogen iodide. The first one is a liquid and the rest are gases. So hydrogen fluoride is a liquid at room temperature and in its normal standard state, and then the rest are gases. Hydrogen chloride, hydrogen bromide, and hydrogen iodide are gases. Please don't confuse them with acids. These are hydrides. Without dissolving them in water, they are not dissolved in water, they are in their normal states. And I proceed. Mary, can you read for us this question?
Explain why hydrogen fluoride is a liquid at 19 degrees centigrade, whereas hydrogen bromide is a gas at the same temperature.
Who can try to approach that question? Linda is saying we also want to read the questions. Yes, Linda, read for us that question. The problem is that most of you are quiet, and when I call you, you don't respond. So sometimes I assume you're not Sometimes I assume you switch on the Zoom, leave it there, and then go do other things so that we think you are present. And the others are as if they are forced to attend the lessons. But that put aside, I'll call you Linda to read the next question. So why is hydrogen fluoride a liquid at 19 degrees Celsius, whereas hydrogen bromide is a gas at the same temperature? You can try to approach the question. This is a question that requires your knowledge on bonding and structure. We have just seen it here. It's already seen here. This is a liquid at room temperature. The rest are gases. What explains that? Yes, Gideon.
Fluorine has a lower molecular mass than the rest of the compounds.
Oh, that's a good trial, but this is not fluorine. It's hydrogen fluoride.
Oh, sorry.
Let's look at the answer and see. But before you look at the answer, I want to teach you how to approach these questions. The first thing you do is to look at the two. Both are hydrogen halides. The difference here is the fluoride and bromide. Okay. So the hydrogens bonded to fluorine and the hydrogens bonded to bromine. Both of these are covalent compounds. None of them is ionic. So how do we approach this question? The answer will lie in this fluorine that is present in hydrogen fluoride. So what shall we say? The fluorine atom is more electronegative and also has a smaller atomic radius than the bromine atom. That's the first thing you'll have to tell me in case the question is given to you. The fluorine atom is more electronegative and also has a smaller atomic radius. Mind you, you're not supposed to say the fluoride ion here. Some of you may think we shall use fluoride ion because it's hydrogen bonded to fluorine. And because of the fluoride, you call it a fluoride ion. Remember, these compounds do not ionize. They are not ionic. They are covalent. So we say fluorine atom in hydrogen fluoride is more electronegative and has a small atomic radius than the bromine atom in hydrogen bromide. And so what? That makes the hydrogen fluorine bond more polar. When an atom is more electronegative than another atom, and the two atoms are bonded to the same other atom, then the bond in which you have a more electronegative atom is more polar. So the hydrogen fluorine bond is more polar than the hydrogen bromine bond. If a bond is highly polar, and that bond is between hydrogen and another element, there is a high tendency of formation of intermolecular hydrogen bonds, which are strong. So the molecules of hydrogen fluoride are held by stronger intermolecular hydrogen bonds, which keep the molecules closer to each other. Whereas the molecules of hydrogen bromide are held by weak van der Waals forces that keep the molecules far apart. Is that fine? Linda, can you read for us the explanation just to emphasize it?
Yes, teacher. Fluorine atom is more electronegative and also has a smaller atomic radius than the bromine.
What is the first marking point in the answer?
Yes.
What's the first marking point in the answer? The fluorine atom being more electronegative, right?
Yes.
So whatever you see red, whatever you see in red ink is a marking point I should always give in your answer. So you go ahead and read the explanation.
This makes the hydrogen fluorine bond more polar than the hydrogen bromine bond. The molecules of hydrogen fluoride are held by stronger intermolecular hydrogen bonds, which keep the molecules closer to each other, whereas the molecules of hydrogen bromide are held by weak van der Waals forces that keep the molecules far apart.
Yeah, those weak van der Waals forces are overcome at room temperature. They are easily overcome at room temperature, so they keep the molecules far apart. Victor, is this clear? Can we proceed?
Yes, teacher, we can proceed.
Okay. Let's look at the methods of preparation of these hydrides. The first method of preparation is what we looked under, reactions of the elements with hydrogen. So fluorine is reacted with hydrogen, forming hydrogen fluoride. Chlorine with hydrogen and the mixture heated or exposed to sunlight form hydrogen chloride. Bromine heated with hydrogen in presence of platinum catalyst form hydrogen bromide, and iodine in a similar way. So you remember those reactions when we are reacting hydrogen with the elements. That's one method that you can use to prepare the hydrides. You can give it in a general way as shown by the equation there. There is another method here whereby we use a concentrated sulfuric acid and the halide salts. For example, if you want hydrogen fluoride liquid in the laboratory, how can we best prepare it? Hallelujah, how can we best prepare hydrogen fluoride in the laboratory? Glenn, how can we prepare hydrogen fluoride in the laboratory? Please call me later. I'm engaged. Call me later. Hello? Hilda, how can we best prepare hydrogen fluoride in the laboratory? Sorry for that mishap. Gideon, how can we prepare hydrogen fluoride in the laboratory? Mary, how can we prepare hydrogen fluoride in the laboratory?
Hydrogen fluoride can best be formed by reaction between cold concentrated sulfuric acid and calcium fluoride.
Yes, that's the best way you can prepare hydrogen fluoride in the laboratory. Note these conditions. The sulfuric acid should be cold and concentrated. If we are preparing hydrogen fluoride, becomes hot for other hydrogen halides or hydrides. So with hydrogen fluoride, we should use cold concentrated sulfuric acid. With calcium fluoride, form the calcium sulfate and hydrogen fluoride liquid. Katz Victor, how can we prepare hydrogen chloride in the laboratory?
Hydrogen chloride is also best formed by heating concentrated sulfuric acid with either solid potassium chloride.
Is it my network or Victor's network? Jeremiah, how can we prepare hydrogen chloride in the laboratory?
Hydrogen with either sodium potassium chloride or sodium chloride.
So it's best formed by heating concentrated sulfuric acid with either solid potassium chloride or solid sodium. Note the products here. So we are using corn sulfuric acid, the liquid, with each of the solid halide salts, form hydrogen sulfates, corresponding hydrogen sulfates, and the corresponding gases. Any of the two can be used. There is a however here. This method is inconvenient. Prepare the remaining two. That's hydrogen bromide and hydrogen iodide, because they are progressively stronger reducing agents. So each of the two, when formed, they will end up reducing sulfuric acid. They will end up reacting with sulfuric acid to form instead bromine and iodine respectively, as we shall see later. The other method is here. The hydrolysis of corresponding phosphorus trihalides prepared in situ. So the best method, this is the best method for hydrogen bromide and hydrogen iodide. Want hydrogen bromide or hydrogen iodide, these are the best methods we can use. So for hydrogen bromide, we add bromine to a paste of red phosphorus and water, forming phosphorus 3 bromide, as you see here. Phosphorus paste with water, red phosphorus, reacted with bromine, form phosphorus tri-bromide. The phosphorus tri-bromide is then hydrolyzed to form phosphorus acid and the hydrogen bromide gas. A similar reaction is done with preparation of hydrogen iodide. We use the iodine, the mixture of red phosphorus and iodine. We get that mixture and add water to it. At the end, we shall get a hydrogen iodide. Note that each of these two reactions does not need any heating. There is no heating is required. So we have seen that each hydrogen halide or each hydride has the best method of its preparation. For example, if we want hydrogen fluoride, this is its best method for lab preparation. If you want hydrogen chloride, these are the best methods. This is the best method. If we want the last two, these are the best methods that we can use. So in each case, if they want each specifically, we must know the best method for each preparation. Now I have a question here. Who can read for us that question? Can it be Arnold Patrick? Yes, sir, Wera. Hallelujah.
Yes, teacher.
Your hand is up. What's the issue?
I want to read the question.
Yes, you go ahead.
Which question is it exactly? The one with B.
Yes.
Okay. Hydrogen chloride can be prepared by the action of concentrated sulfuric acid on potassium chloride, but hydrogen iodide and hydrogen bromide cannot be prepared by the action of concentrated sulfuric acid on potassium iodide and potassium bromide respectively. But teacher, is that the question?
Hey, there wasn't a word explained. In other words, we are explaining that question. It's a statement that needs
Explain.
So potassium chloride reacts with the concentrated sulfuric acid to form hydrogen chloride gas. Potassium chloride reacts with sulfuric acid to form hydrogen chloride gas. You see this equation? Yes. This hydrogen chloride gas is a weak reducing agent. It's a weak reducing agent due to the small atomic radius of chlorine atom. You'll change this in your notes. Due to the small atomic radius. These are covalent compounds, so don't talk about the ionic radius. So form hydrogen chloride gas, which is a weak reducing agent due to smaller atomic radius of the chlorine atom. That's why this one cannot, the hydrogen chloride cannot reduce the sulfuric acid. So the reaction ends there. However, on the other hand, if these two react, if we react potassium iodide and potassium bromide with sulfuric acid, the reaction, it's true, will form the hydrogen iodide and hydrogen bromide respectively. But it doesn't end there. The hydrogen iodide and hydrogen bromide formed as strong reducing agents, and hence reduce sulfuric acid to sulfur dioxide as they are oxidized to iodine and bromine respectively, due to the large atomic radius of iodine and bromine atoms. So they are oxidized to iodine and bromine respectively. So the iodine here is observed as purple vapors in case you ask the observation, and bromine is observed as reddish brown vapors. Look at the two equations. Molecular equations are better here because they can easily be balanced to accompany your explanation. So the reason as to why this reaction can occur is because the hydrogen chloride is a weak reducing agent. It can't reduce the sulfuric acid to sulfur dioxide, and for it to be oxidized to chlorine gas. However, the hydrogen iodide formed in each of the second cases is a stronger, they are strong reducing agents, so they reduce the sulfuric acid to sulfur dioxide and water as they are oxidized to vapors, bromine vapors and iodine vapors. So these are vapors in this case. This is not a liquid and this is not a solid due to the high temperatures. The reaction normally occurs with heating. And even if we don't heat, the reaction itself may liberate heat that will make these vapors. And those vapors can easily be observed in the laboratory. Are we together, members? Are we together? Yes, we are together. Okay. So in case we can see one of the two reactions, it's here. I want you to observe carefully and see what happens when each of the, yes, hallelujah, you have a question.
Grammarly is your personal writing assistant for clear
First keep
emails,
that question
confident
and then we
messages,
see this first.
stronger essays, and more. Because sometimes the kitchen.
So these reactions are carried out in a fume cupboard because they are so that indicator there is changing to blue, showing that there's an evolution. Effervescence is observed with the evolution of colorless gas, which is hydrogen chloride gas. The white residue is sodium hydrogen sulfate. Look at what happens when sulfuric acid is added to sodium iodide. So sodium iodide is added sulfuric acid. Look at what happens. I hope you see the brown vapors being formed. They are brown, but I expect them to be purple. They are normally purple vapors being formed with the sulfuric acid. The reaction also sometimes forms hydrogen sulfide, and sometimes forms the sulfur. The yellow you see here is due to formation of sulfur. You can very well see it on your screen. So they used lead ethanol here to confirm the presence of hydrogen sulfide as part of the reaction. So purple vapor of iodine is observed. Iodine crystals are formed higher up in the test tube after sublimation. The purple vapors then sublime, form the iodine crystals. But normally for us, we are interested in the purple vapors. Look at the last reaction between sodium bromide and sulfuric acid. So the potassium dichromate here is test for the sulfur dioxide that will be formed as a result of that reaction. It's an orange solution. It will turn green, confirming sulfur dioxide being evolved as part of the reaction. Sulfuric acid is added to the sodium bromide, as you see. So hope you see in that reaction that there are brown vapors being formed. You can see the brown vapors here. Brown vapors are vapors of, I don't know why the color is brown. They are normally reddish brown. I think, yeah, reddish brown is okay. Here there are purple vapors being formed with the sodium iodide. So you see this good pale green here. The pale green is due to the pale green. So you see the orange brown fumes of bromine are observed. He called them orange brown. We call them reddish brown at our level. And then the paper turned green. The orange potassium dichromate paper turned
We all know the
green.
crazy chaos caused by trying to use more than one app for productivity. There has
So we shall see other reactions some other time. I hope you've got that clearly. You can allow me now to proceed. And yes, there is a question from any of you. Is there any question from anyone? Is there any question from anyone so far? So here we have been, and those are the reactions I've been looking at in that video. Can I proceed?
Yes.
Teacher,
Yes, please.
kindly please do a recap in this
I'm not getting you, Aweda.
This
Is it the network, or I don't know why I'm not getting your voice? You type in the chat box, type your question there. I'll answer it. So we proceed to melting and boiling points. Explain the trend in boiling points of the hydrides. Those boiling points are also explained in terms of bonding and structure. They generally increase from hydrogen fluoride to hydrogen iodide, with hydrogen fluoride having an abnormally high value of boiling point. This value is abnormally high. It's very positive, whereas the others are negative. So the increase in melting point from these three here, we look at them separately. It's because the three hydrides have simple molecular structures held by weak van der Waals forces, whose magnitude increases with increasing molecular weight, leading to an increasing amount of energy required to break the forces of attraction. Okay? Yes. So, how about the hydrogen fluoride? It's a unique one. It has an abnormally high value of boiling point because the fluorine atom in it is more electronegative and has a small atomic radius than the iodine atom in hydrogen. Did I write that anywhere? I don't have it anywhere. Yeah, this is it. Hydrogen fluoride has an abnormally high melting point because the fluorine atom has the smallest atomic radius and highest electronegativity. So that makes the hydrogen fluorine bond highly polar. We have already seen that. And that results into the molecules being held by strong intermolecular hydrogen bonds, which require a high amount of energy to break. I think this is not new and is not confusing to any of you. Am I clear? Then I can proceed to the former question here. It's a comparison question. Explain why. Linda, you read for us this question. How will you mute your mic? Linda, can you read for us this question?
Explain why hydrogen.
Linda, please read the question.
Explain why hydrogen fluoride has a higher boiling point than hydrogen iodide.
Yes. Explain why hydrogen fluoride has a higher boiling point than hydrogen iodide. So the fluorine atom in hydrogen fluoride is more electronegative and has a small atomic radius. I'm repeating this almost for the third time. It's more electronegative and has a small atomic radius than the iodine atom in hydrogen iodide. So that makes the hydrogen fluorine bond more polar than the hydrogen iodine bond. The molecules in hydrogen fluoride are held by stronger intermolecular hydrogen bonds, which require a high amount of energy to break. Whereas the molecules in hydrogen iodide are held by weak van der Waals forces of attraction that require a low amount of energy to break. So that concept should be understood by most of you. Thermostability of the hydrides decreases in that order. So as you move from hydrogen fluoride to hydrogen iodide, the thermostability is the effect of heat or stability in terms of the effect of increasing temperatures on of the hydrides. So the thermal stability decreases because the atomic radius of the halogen atoms increases from fluorine to iodine, and that makes the hydrogen halogen bond length longer, which reduces its strength. So when the strength reduces, when the length increases and the strength reduces, those bonds can easily be dissociated with the increase in temperature. Shouldn't waste a lot of time on that. Acid strength, you haven't looked at ionic equilibria, but you should know that strength of an acid depends on the number of hydrogen ions produced in solution, in its solution. So this acid dissociation constant denote the acid strength of the hydrides, meaning that hydrofluoric acid is the strongest acid, followed by hydrogen chloride, and then hydrogen bromide. Okay. No, hydrogen fluoride is the weakest acid because this value is the smallest, and this value is the highest. That means hydrogen iodide is the strongest acid. So the Ka values increase in that order, indicating that the acid strength increases in the same order. The acid strength is explained in terms of bond length and bond strength for these hydrides. So as the atomic radius of the halogen atoms increases from the fluorine atom to the iodine atom, the hydrogen halogen bond becomes longer, reducing yeah, Mary is asking a question. Mary, I'll answer that question when we look at group 7. So this makes the halogen bond longer, reducing the strength, and that's from hydrogen fluoride to hydrogen iodide, releasing many hydrogen ions. So when the hydrogen ions released are very many, then the acid becomes stronger. However, hydrofluoric acid is the weakest acid because the fluorine atom is the most electronegative, and the fluorine atom also has the smallest atomic radius. That makes the hydrogen fluorine bond the shortest and the strongest. And hence hydrofluoric acid dissociates to a considerably smaller extent. Who else wants to read this question? Here is another question. Yes, Linda, you read. You love reading so much. Linda, you can read the question.
Explain why hydrofluoric acid is a weaker acid than hydroiodic acid.
And iodic acid. Some people call this hydrogen iodide. It becomes iodic acid when the hydrogen iodide, when the hydrogen iodide is dissolved in water. But when it's still in its normal physical state of a gas, then it's not an acid. So the fluorine atom is more electronegative than the iodine atom and has a small atomic radius than the iodine atom. That implies the hydrogen fluorine bond is shorter, more polar, and stronger than the hydrogen iodine bond. So the hydrogen fluorine bond does not easily break, releasing fewer hydrogen ions in solution than the hydrogen iodine bond, which is longer, weaker. It is longer and weaker, of course. Hence releases very many hydrogen ions, or more hydrogen ions compared to hydrogen fluoride, hydrofluoric acid in the solution. Are we together? Mary, can you read this answer for emphasis?
The fluorine atom is more.
Mary reads.
The fluorine.
Somebody is raising up a hand. Is it Linda? Mary, go on.
The fluorine atom is more electronegative than the iodine atom and has a smaller atomic radius than the iodine atom. Therefore, the hydrogen-fluorine bond is shorter, more polar, and stronger than the hydrogen-iodine bond. The hydrogen-fluorine bond, therefore, does not easily break fewer hydrogen ions in solution than the hydrogen-iodine bond, which easily breaks.
That's very correct. Okay, that's all about acid strengths of the hydrides. This topic is coming to completion. The anomalous behavior of fluorine. Normally they ask you, we have seen so many cases where fluorine is behaving uniquely, and even the hydrogen fluoride. Now there are reasons as why fluorine behaves uniquely compared to the other elements. Okay. The reasons are basically 5. And if it's an exam, I want you to give the first 2, always be cautious with the third one. The third one, even some examiners mention it wrongly. Normally, say fluorine has an abnormally lowest value of bond dissociation energy, which is not true. Iodine has an exceptionally lower, actually, iodine has a lower value of bond dissociation than fluorine. You check your notes and see that. So it's better always give the first one, second one, fourth one, and fifth one, in case you're asked. And normally use the superlative format, smallest, highest, largest, because you are always comparing it with other elements if you want to get the marks. If you want to lose the marks, you say fluorine has a smaller, fluorine has a small. There you're not comparing with the other elements. So the superlative format is normally used in these comparisons with the other elements. Linda, can you give 3 reasons as to why fluorine behaves anomalously compared to the other elements in group 7? Give 3 reasons.
Fluorine atom has the smallest ionic radius compared to the other elements.
That's
Then
wrong. That's wrong, Linda. Read the correct. Give me the correct answer, please. You said ionic radius. It's wrong. Fluorine is not an ion.
No, fluorine atom has the smallest atomic radius compared to others.
1 mark. Another one.
Fluorine atom has the highest electronegativity among the other elements.
2 marks. Another one.
Fluorine has the largest positive standard electrode potential among.
Very good. 3 marks. Gideon, apart from atomic radius and electronegativity, can you give any 3 reasons as to why fluorine behaves anomalously compared to other halogens? Apart from atomic radius and electronegativity differences, give 3 reasons as to why fluorine behaves different compared to other halogens. Gideon.
A fluorine molecule has an abnormally low value of bond dissociation energy of the fluorine bond. Unlike other elements, fluorine atom cannot expand its octet.
Another one. Okay, that's very correct. Let's proceed. To the last bit of this lesson. These are ways or properties. I want you to differentiate the reasons and the properties. So these are the properties in which fluorine behaves anomalously. In other words, if they talk about properties, they are talking of reactions. If they talk about reasons for anomalous behavior, they are the ones we have just seen. Katz Victor, what's the first property that distinguishes fluorine from other halogens?
Fluorine oxidizes water to oxygen and itself reduced to
hydrofluoric acid.
Hydrofluoric acid. Iodine does not react with water and other halogens. Is
proportionate to water. Okay. Now you listen to me carefully here. If they talk about anomalous properties of fluorine compared to the other elements, you must not only talk of fluorine, also talk about what happens with other elements. That's why you see these second statements. Is that clear? Frida, what's the second property in which fluorine behaves differently from other elements? Hello, Lava. Frida is not there. Rebecca, which is the other property in which fluorine behaves differently from the other elements?
Teacher, me.
I've been up for so long. I don't even know where we are.
Teacher, let me read it.
Read the Frida. Rebecca has not been following. Frida, I'm waiting.
Third one, the second one.
I don't know. I'm asking you, it was a question. Give me any property in which fluorine behaves anomalously from other halogens, apart from the one who's already given.
I don't know.
You see? People are not following. Yes, Glenn. Your voice is not heard well, Glenn.
Fluoride ion, other halogen is proportionate from alike.
Yes. We have heard that. Jeremiah, can you give me any other anomalous property of fluorine compared to the other elements? Linda, can you give me any other property?
Fluorine combines directly with carbon. Other halogens do not react directly with carbon.
All right. So you should note that those are the anomalous properties in which fluorine behaves differently compared to the other elements. Now in your notes, read about these remaining things here. Polarizability of the halide ions, qualitative analysis of chloride, bromide, and iodide ions. You have the notes. You'll do them practically when school resumes. You do them, those tests practically. Attempt all the 22 miscellaneous topical questions. Group 7 is done. Group 4 will be our next topic. Is that very clear?
Yes, teacher, thank you for the lesson.
You're welcome.
Teacher,
Yes, please.
I have been recording the lesson, right?
Yes, but I will not send the recording.
Teacher, but why? Because some of us, the network has really been very poor, so we have not been following.
Yes, those people who don't want to attend the lessons, when they get recordings, they feel very happy that they always get recordings. So I've not sent the recording to you. Why haven't you been following, Rebecca?
Teacher, the network has been on and off, on and off.
Oh, sorry. We shall see what to do. Thanks, everyone. We meet next time.